and show you the simulation that we have. This simulation is built in a product called Extend that we use at MoreSteam, as well as, and it's a discrete event simulation engine. And this type of process simulation modeling, as well as process optimization modeling, is a central component of the Master Black Belt program at Ohio State University and MoreSteam. We're really learning the nuances and the depth of the Lean tools by building simulations of them. So we learn both how to model our processes, as well as some of the nuances and intricacies of the Lean tools by using these types of simulations. So in this simulation, and I'll start it going here, in this simulation here, we see a number of different things happening. We have, on the top of this simulation, we have a push system where we're, by forecast, pushing work into this process, this three-step process. And on the bottom, we have a core process pull, a pull system. Now, both processes are receiving the same customer demand inputs. So you'll see customers that just appeared here, and they pulled their finished goods out of these two buffers. Here's a finished good item here. Here's a finished good item with a Kanban card attached to it below. And the customers are pulling those away. And you'll see that the customer demand comes identically to both processes here. It's randomly generated, but it comes identically to both processes. The forecast varies between 3, 4, and 5 units that are going to be showing up and pushed into the process, and that is exactly at the average consumption capacity demand rate for the process. So they really are very identical processes in terms of their demand and the randomness of that demand and the randomness of the service times. In the above process, we're pushing work in. Our bottleneck, which is our middle station here, will end up being backlogged, and work will continue to push onto that person even though they're backlogged, versus our core process pull system here, which is just sized for 3 pieces of WIP with our 3 Kanban cards. And you'll see in the bottom process here that we're not getting excess WIP pushed into the system because we don't get to start new work until this Kanban card here on the right gets pulled off of that inventory and flies back over to the left and authorizes the beginning of work at our first station. If you look at our results over on the right here, we'll see that sales is equal to 10 for both of them. Right now, average weight for the customer is still 0. We haven't had any delays in meeting customer needs. The inventory for the push system is at 5.2 versus 2.4 for the pull system. And our total cycle time or total lead time through the process, because of that excess WIP, is at 3.9 for the push system and at 2.5 for the pull system. Now we're just at sales of 13 here. I'm going to turn the animation on and off, or off and on, just for a moment so we can kind of jump further down in time in this process. So flip it off and flip it back on again. Now you can see we're up to 751 in sales. So it runs very quickly without the animation on. What we have now is we've got a whole line of customers that are queued up behind our push system here, waiting for inventory, waiting for finished goods. We don't have anybody queued up on our pull system. Our average inventory of our pull system is still at 2.5 because, again, it can never go above 3 because we only have 3 Kanban cards. Average inventory in our push system is higher, yet still we have an average weight of 10 here, average weight of 0.009. Now, this process is actually sized at about 95% utilization. So that's a fairly high utilization rate, and in a high utilization system like that, any lack of work at the bottleneck is going to cause a process to lose that capacity and have a tough time ever catching up with that again. And in a push system, we have no mechanism for really managing that WIP and keeping it in the right place. As processes get lower and lower utilization, so if we're down in the 50 or 60% utilization range, the impact is less severe. But certainly in transactional world, we're tending to look at processes that are designed to be very highly utilized. And in the manufacturing world, we're shooting for higher and higher productivity as well, and therefore higher and higher utilization. And it becomes more and more difficult to very carefully manage the WIP and how that WIP moves and when work is authorized. Ideally, we will have a system where the lead time that it takes to get through our process steps, however many process steps that may be, that lead time, our normal lead time for any product or service to get through those steps of our process, is so short that it's short enough to meet customer expectations of that total lead time, even if those expectations change. When we get to that level of performance, our customer expectations and our customer demand, our voice of customer, can change as often as it wants, and we simply introduce that change as the next item going through our process, rather than in this top scenario here, where we have excess WIP already in the process that we would have to work our way through, and excess lead time before we'd actually be able to get those new customer demands and that new voice of customer reflected in the output of our process. So we use simulation like this, and we learn about process simulation, both discrete event simulations like this, as well as mathematical optimizations, and that becomes that's a key component of the Master Black Belt course at Ohio State University. So let me stop this and hop back over to our PowerPoint presentation. And then I think, Larry, we're probably ready to